Hello everyone, welcome to our poster presentation. We will discuss our work using evolvable bones in modular robots. We give the robots the ability to evolve the length of their bones and observe how the length of the bone influences their fitness performance. Our study investigates the impact of adding evolvable length bones to modular robots. By running simulations, we analyze how both morphology and behavior co-evolve across generations. We test two different fitness strategies and then compare the result in both simulation and reality. To validate what we found, we physically built one of the high-performing robots and compared its real-world movement to its simulated twin. In this image, you can see our physically built robot on the left and our simulated robot in Revolve 2 on the right. This work is driven by three core questions. 1. Is the ability to change the length of the bones utilized by evolution? And how does the modular length change over successive generations? 2. Do robots with evolvable modules outperform those with fixed size modules under the same fitness criteria? And 3. How does the design of the fitness function affect the outcomes? These questions guided the setup and analysis of our experiments. We used Revolve 2, a modular robot simulation platform built on GECCO. Two bone types were compared, a standard fixed length bone and a new evolvable bone adjustable from 75 to 225 mm. We also explored two fitness strategies, a combined function that optimizes height and displacement simultaneously, and a split function that optimizes them in sequence, first height then displacement. This setup allowed us to test how different pressures affect the evolution of bone length and movement. Now, let's look at our outcomes. The left graph shows bone length over generations. In both fitness setups, bone length quickly increases, showing that evolution does utilize the ability to grow bones. In the split fitness peaks during height optimization and drops after switching to displacement. Eventually, it will stabilize and go on. In contrast, the combined fitness method leads to more consistent and longer fitness throughout. There are three takeaways from the fitness performance graphs. First, with the split method we observe a fitness drop after a switch from height to movement, but evolvable robots still retain an edge. Second, the combined methods perform more steadily overall, and statistical tests confirm that longer bones correlate with higher fitness. Finally, robots with evolvable bones consistently outperform fixed-size robots across both fitness strategies. As also seen on the current graph for the combined fitness function, robots with larger bones have a general higher fitness. We built one of the top robots in real life and compared it to the simulated version. The movement patterns are similar overall, both show a clear up and down trajectory. However, the real robot's motion is less smooth, and its fitness is lower, about 2.03 compared to 3.07 in simulation. This reflects the reality gap. Real-world issues like friction, motor imperfections that we couldn't comprehend or account for are present. Here are our takeaways. Evolution consistently favors longer bones. When height and displacements are optimized together, even when fitness objectives change mid-run, evolution adapts and finds a new balance. And finally, there is a strong positive correlation between bone length and performance, confirming the evolutionary advantage of longer adaptable structures. Thank you for watching and listening. If you'd like to export the paper or code in more detail, feel free to scan the QR codes.